Today we are going to discuss in our discussion about work, power, energy, kinetic energy, conservative force, non-conservative force, and potential energy. Let us start with work. If we know there is a body and we applied a force on it, and this force is external force, we are not considering, or we are not taking the internal forces in between the particles due to their gravitational interaction or due to the electrostatic repulsion. We are taking the external push and pull. And if the body is sliding or shows some displacement in the direction of the force, then we very well know that the work is given as the dot product of the force and the displacement. If displacement is very small, then we know the work comes out to be small. The displacement and force direction should be same, but in every case that is not possible. At that time we take only the component of the force which is in the direction of displacement. Let us consider that case also. Let us consider we have applied the force in this direction. This is the direction of the force applied, and the body is moving or showing displacement in this direction. This is the displacement direction, and the angle in between the force and the displacement direction is theta. Now, what is the component of the force in the direction of displacement? You can very easily calculate this. If force is a vector quantity and making an angle of theta with the horizontal, we very well know that the horizontal component of the force is F cos theta, and the vertical component of the force is F sin theta. And we are talking about the component which is along the direction of displacement, and in our case the horizontal component is in the direction of the displacement. Hence we will take in this case force as F cos theta, because only the F cos theta component is working to displace the body from A to B with displacement ds. And if F is the magnitude of the force and ds is the magnitude of the displacement, they can be given in vector form, and in vector form we can give in the dot product form, that is F dot s or F dot ds, because the displacement we have taken is very small. If we open F dot ds, we will find we have to give the magnitude of F with magnitude of ds and the cosine of the angle, smallest angle in between them. And if we open this, we will get F ds cos theta. So this is how the work is related with force and displacement. If we have to calculate the total amount of work done, then if the force is constant, then we can very easily calculate for constant force. It means if a body is moving from point A to point B and showing a displacement of S, and a constant force is applied on this body, then we can easily find out the work. The work comes out to be the multiple of F and S if they both are in the same direction. But if the force is variable, if the force is changing from position to position or time to time, then we can take the integral of the displacement, how many parts, in how many parts the displacement is divided, and then we integrate from its initial position to the final position, and we can easily find out the total work done. It means the work done. How will you calculate work done? It depends whether the given force is constant or whether the given force is variable. If the given force is constant, then you can directly multiply force into displacement if both are in the same direction. But if the force is variable, just to divide the whole part in small parts and integrate the small parts from initial position to the final position. Next, physical quantity that is related with work is power. How much work you will do in 1 second, that is known as power. It means power is nothing, it is the total amount of work done in total interval of time, and its unit is joule per second, or also we say that the unit of the power is watt. Power can be related with force and velocity. If small work is done in small interval of time, then we can from above relation put work as F dot ds, and here it is divided by dt. ds upon dt, that is displacement upon time taken. This is nothing, it is your velocity. It means if we have to calculate power, if work and velocity vectors, force and velocity vectors are given, we can dot product them and we can easily find out power. Otherwise, you can find out the work done in unit interval of time, that is again power. Next topic of our interest is energy. Energy of a particle, it is capacity of doing work, and it depends the work is done by changing the velocity or by changing the position. Hence, energy is of two types. If the body is in motion, then the energy of the body is known as kinetic energy. And kinetic energy is given by half of mass and square of the velocity. That is the formula. T is equal to, or kinetic energy is equal to half mv square. And in many reference books or in many textbooks, the kinetic energy is indicated by capital T. There is a relation between kinetic energy and work. How we are going to find it out? Let us consider a particle is moving from first point 1 to point 2, applied a force F and showing a displacement of ds. Then we can easily give work done as F dot ds, integrating it with from initial position 1 to the final position 2. From the second law of Newton's motion, there is a relation between momentum and force, which is given by F is equal to rate of change of momentum. That is, F is equal to dp upon dt, and the direction of momentum, change of momentum, is the direction of force. We can substitute this in the above relation and you will have dp upon dt dot with ds, and dp upon dt dot with ds. We can again substitute the value of momentum here, that is mass into velocity. Substitute this in the above relation. Mass is a constant quantity, it will not change with time. It means the differentiation here will come to the velocity. We will get dv upon dt here. Substitute the value of momentum in terms of mass and velocity. You will have m dv upon dt dot ds from initial point to the final position, that is 2. Now ds upon dt, that is velocity, you can put it m v and here dot with dv, and we know that change in velocity v dot dv, that is that magnitude of v, magnitude of change in velocity, and cosine of theta from first to the second position, or we can say that from one final initial position to the final position. Now integrating velocity here, we will get m v square by 2, the power of the velocity increased by 1, and with this number we will divide the velocity, square of the velocity, and the initial value of the velocity, let us consider at point 1, position 1, the value of the velocity of the particle is v1, and at the final position let us consider the velocity value for the particle is v2. Putting the upper limit first and lower limit second with negative sign, you will have half of m v2 square minus half of m v1 square. Half of m v square, that is kinetic energy, half of m v2 square, that is kinetic energy again, but it is our final kinetic energy, and half of mv1 square, it is indicating the kinetic energy at initial point or initial position of the body. It means we are giving the difference of kinetic energy, and this difference of kinetic energy, it is nothing, it is equal to work. This is our work, and this relation in between kinetic energy and work, this is known as work energy theorem. So what is work energy theorem? Work energy theorem, it indicates that the change in the kinetic energy is equal to the work done. If someone asks you about there is a change in the kinetic energy and how much change is there in the kinetic energy, we can easily say that change in the kinetic energy is equal to the work done by the body or work on the body. It means work can be given as change in the kinetic energy. This is the relation between kinetic energy and work done. Next, we will discuss about the relation in between work and force. If we discuss about conservative forces, in case of conservative forces, let us consider we applied conservative force on this body, and this body moves from point 1 or position 1 to position 2. Then how we will define conservative force? Conservative force, it is the force, the work done by which depends upon the initial position and final position. It does not depends upon the path followed by the body. If you are moving the body from first path, in our case from second path or from third path, if the applied force is a conservative force, in every case, the work done comes out to be same. Let us consider the work done is W in our case. Then, in if the body cover the first path, the work done will be W. If body covers second path, again it will be W. And if the body covers the third path, again the work will be W. It means if we are discussing about conservative forces, the work done by the forces, these type of forces depends only on the initial position and the final position. It does not depend upon the path followed by the body. The actual path followed by the body is longer. Second path is longer as compared to the first. Third path is longer as compared to second. But in all the cases, the work done, or we can say that the initial and the final positions are same, hence the work done is same in all the three paths. Here the work done is given as force again into displacement if we divide the whole path into small partitions or small divisions. And if the force is conservative one, then we can say that for a closed loop, let us consider the case if the particle moves from A to B due to conservative force, and again if we move it from B to C, again the applied force is conservative, then for the first path, what will be the work done from A to B? The work done from A to B is given by F dot ds. Then let us consider the small parts of this path is represented by ds, and the initial position is A and the final position is B. Again, if we consider the work done of this given body from B to A, it is given by again F dot ds from B to A. If we interchange the limits, we very well know that if A becomes the lower limit and B becomes the upper limit, we have to change the sign of the integral. And if we find out the total work done from A to B and from B to A, we will find out that the total work done will be equal to 0 in our case. And this total work done here is given by F dot ds. Condition is that the given force is conservative and the body is moving in a closed loop. If body is moving in a closed loop and applied force is conservative, only then the work done by this conservative force is equal to 0. This is the conclusion of conservative forces. These are the forces which are not depending upon the path followed by the body. The work done by these forces does not depend upon the path followed by the body. The work done depend upon the initial position and the final position. Second, if the body is moving in a closed path and the body is experiencing a conservative force, again the work done by these type of forces in a closed loop is equal to 0. It means if a particle is moving in a closed loop or in a showing a rotational motion or moving in a circle from moving from point A to complete a rotation and again come to point A, the work done in this case is equal to 0 if the applied force is conservative one. Next, we are going to discuss about non-conservative forces. Non-conservative forces are opposite of conservative forces. Here, in this case, if the body is experiencing non-conservative force, then the work done by these forces depends upon the path followed by the body. Again, consider the same case. If a body is moving from A to B and experiencing a non-conservative force and having a displacement S, and this displacement is divided into small parts, that is ds. Let us consider this is the first path followed by the body. Let us consider this is the second path followed by the body moving from A to B, and again consider this is the third path. Then for every case the work done will be different if the force is non-conservative one. For the first path, the work done is W1 and from A to B, and this is our work done in case of the body if it is experiencing a non-conservative force. Similarly, Here we will take the actual path followed by the body. In first case, the path is the smallest one. In second case, the path will be larger one, and in the third case, it is the largest one. Here, the work done in all the three cases depends upon the actual path followed by the body. Here, the work done is not depending upon the initial position and the final position. Similarly, if we have taken a closed path, if a body is moving from B to A and from A to B to B to A, here the work done for the first path is W1 and the work done for the second path is W2, and the total work done is W1 plus W2, and that is not equal to 0 in our case because the applied forces are non-conservative in this case. So the work done for non-conservative forces for a closed path is not equal to 0. It is always greater than 0. It is always positive in nature. So what are the type of the forces which are conservative and which are the forces which are not conservative or non-conservative? In conservative forces, we have a lot of examples. Gravitational force, it is an example of conservative force because in gravitational force, the force depends upon the initial position and the final position. That is the distance between the centers of the two objects. In magnetostatic forces, again, if this is north pole, this is south pole, then there is some attraction. Then from pole to pole distance, these 2 points are fixed points, and here again the conservative force upon depends upon the initial position and the final position. For non-conservative forces, consider those forces which depends upon the path followed. Here, in case of non-conservative forces, the friction force is the most common example of non-conservative force. In frictional force, the work done depends upon the in path followed by the body. The friction force depends the actual distance covered by the body and two surfaces, how much they remain in contact, for how much distance they are remaining in contact, and due to the path there is a force, and this force is not depending upon the work done by this force is not depending upon the initial position and final position. It depends only on the distance covered or actual path followed by the body. Now we will discuss about potential energy. Potential energy, it is the energy due to the position of the body. Let us consider a body is at point 1 and its potential energy is V1. And if we move this body from 1 to 2, its potential energy becomes V2 at any position T2, at any position 2. Sometimes this point is taken as a reference point, that is known as zero position point. If this is considered as reference point or zero position point, at this position we consider that the potential energy of the particle is 0, and from this point we calculate the potential energy of the second position, taking this point as a reference point. But there is no position in the universe where the potential energy of the particle is 0. Here only for the calculations or to calculate the potential energy of the second position, we only consider that first position is your zero position energy. Again, energy is work, work is energy. It means here work can be written in the terms of potential energy, as we have written kinetic energy change is equal to work done. If V is the potential energy at point 2, then what is the change in the potential energy? The potential change in the potential energy is V minus 0. That comes out to be V. And this change in the potential energy is given by work, or we can say that work is converted into the potential energy. If work is attached with potential energy, it means there is some relation between force and potential energy. Work is given by F dot ds if the particle is moving from the second position to the first position. But if the particle is moving from first position to the second position, we will give is this like this. Lower limit now will be r1 and upper limit will be r2, and this is F dot ds. This is the relation between potential energy and the force. The potential energy is due to the position of the particle. Here it is a function of the position coordinates x, y and z. If there is a change in the potential energy, it means there is some change in the coordinates, maybe x coordinate change, maybe y coordinate change, maybe z coordinate change. It means potential energy can change with x if there is a change in x. Potential energy show change with y if there is a change in y, and potential energy could change if there is a change in z. It means change of potential energy depends on each coordinate of the position of the potential energy. We can write this in dot product. We can show this as a we can show this in the vector form. The differentiation can be written one side with unit vectors. The unit vector along x-axis is indicated by I cap, along y-axis it is indicated by j cap, and in direction of z it is indicated by k cap. Similarly, the small displacement along x-axis in direction of x, that is indicated by I cap, the direction of y axis indicated by j cap, and similarly the change in along the z direction can be indicated by k cap. Now just go for the dot product. If we multiply these two vectors, we know that in dot product I dot I is equal to 1, I dot j is equal to 0, j dot k is equal to 0. Only the terms change of v with respect to x dx will survive. Change of v with respect to y dy will take place, and change of v with respect to z dz will survive, and these are the terms which we will obtain after multiplying these two vectors. And these two vectors can be written in the form of del operator. If we take common from the above term, from the above bracket, v can be taken as common, then we will have operator like this, and another vector can be represented by ds, where ds is nothing, it is the displacement vector, and it is shown by the displacement along all the three coordinates. Now if we take this term individually without V, it is meaningless. Let us consider I cap change with respect to x, j cap change with respect to y, and k cap change with respect to z. This is nothing, it is an operator like addition, multiplication, and division. This operator is known as del operator, and it is symbolized like this. So the work change in potential energy from this above term, that is your del operator, can be written like this. With V, you are operating this del operator on potential energy and dot with displacement vector. Hence, this is the change of potential energy, which is given like this. If the potential energy or the position of the particle is moving or changing from 1 to 2, then the total potential energy can be given as integration of the small changes in the potential energy or small changes in the position of the particle. And in terms of del operator, if we substitute these values, we will have, that is gradient of V or del of V, that is also known as gradient of V if there is no dot product or no cross product here. If we have a dot symbol here, this is known as divergence. If we have a cross symbol in between del and V, we have curl, uh, curl of the vector here, and this is the displacement vector. Now, from our previous conclusion, we find out that there is a relation in between potential energy and force, and this relation is F is equal to V is equal to minus F dot ds if the particle is moving from 1 to 2, and here is also the particle is moving from 1 to 2. On considering these two equations, what will you get? Both are indicating the potential energy, and from here we find out that F is equal to minus del V, and this is also known as gradient of V with a negative sign. It means the force is in the direction of decreasing of potential energy. Let us consider what this negative sign is indicating. If we have two charges Q1 and Q2, we know that Q1 apply a force on Q2 in this direction. This is the direction of force. And if we move the position of second charge from A to B and from B to C, we are changing the position, then we are changing the potential energy of the second charge. And the potential energy of the second charge is given by 1 upon 4 pi epsilon naught Q1 upon the distance. In first case, the distance is Ra, the smaller one, so potential energy is Va. In second case, the distance is Rb, now the potential energy is Vb, and here the potential energy is given by Q1 divided by Rb, and Rb is greater than Ra. If Rb is greater than Ra, then Va is greater than Vb. Similarly, for the third position, Vc, this is equal to 1 upon 4 pi epsilon naught, and this is Q1 upon Rc, and we know that Rc is greater than Rb and Rb is greater than Ra. This is the relation in between all the three distances. Then what is the relation in between the potential energy? Here V is greater than VB and VB is greater than VC. It means V is the smallest potential energy and VB is the large potential energy and VA is the largest potential energy. Mean potential energy is increasing in this way, or we can say that potential energy is decreasing in the direction of force. So the force is showing the direction of decreasing of potential energy, hence the negative sign indicates the force is in the direction of decreasing of potential energy. How we will give the relation in between initial potential energy, final potential energy and the work done? Here the work done from point 1 to 2, if we shift the particle from position 1 to 2, we will have the work done is equal to F dot ds with lower limit 1 and the upper limit 2. But in case of potential energy, we know that force is given as negative of gradient of potential energy, and this is displacement is taken from there and from position 1 to position 2. From the last page we find out that change a gradient of v dot ds, that is displacement, is nothing that is change in velocity. So sorry, change in potential energy. So for this whole part we can show that is there is a change in potential energy, and we substitute it like that dv from position 1 to position 2. If we integrate it, we get the potential energy, and there is a negative sign. Here the negative sign remains. At position 1 and at position 2, let us consider the potential energy is V1 and the potential energy is V2 in this case. Put the upper limit and lower limit. We will get minus V2 minus V1, or if we rearrange it, we will get potential energy is V1 minus V2. How we will verify it? There is simultaneously change in kinetic energy and potential energy if a body moves from point 1 to 2. Let us consider a body is moving, and at initial position 1 the kinetic energy is k1 and potential energy is v1, and at any second point t 2, that is kinetic energy final is k2 and potential energy is v2. We very well know that the total energy initial and total energy final is equal when there is no external energies applied to the body. If the body is moving by its own, the position is shifting and the kinetic energy is changing. In this case, kinetic energy K1 plus potential energy V1 should be equal to kinetic energy K2 plus potential energy V2. Just rearrange these terms, keep potential energy at one side and kinetic energy at one side. We will get V1 minus V2 is equal to kinetic energy KE2 minus KE1. From here we can find out how work is related with change of potential energy and with change of kinetic energy. Here final kinetic energy minus kinetic energy, it is your work done as we have discussed in work energy theorem, and initial potential energy minus final potential energy, again it is showing work done. It is very obvious that if the kinetic energy increases, let us consider the kinetic energy increased here in this case. It means the body's velocity is increasing. It is speeding up. If the body velocity is increasing, kinetic energy is increasing, it means kinetic energy at initial point is small as compared to the kinetic energy at final point if the body is speeding up. And if the kinetic energy at this point is small, it means potential energy at this point is large because the total sum of these two physical quantities should be a constant quantity. Similarly, here the kinetic energy is large and we have a total constant energy, it means V2 should be small. It means V2 is less than V1 if we are obeying law of conservation of energy. And these are the two relations where we show change in potential energy is equal to the work done by the body or on the body, and change in kinetic energy also is due to the work done by the body or work on the body.